Okay, welcome back. I'm on page 166, and we stopped right here where this line is. And I indicated that I wanted to go over this process that we saw on the bottom of page 165. We'll kind of fast forward, and then I'll come back to those pages that we skipped over. Okay, it's not like we're not going to do those other pages. It's just that I think that once we're talking about this topic here, it's going to put us in a perfect position to go ahead and kind of fast forward on some of this. So if you will, okay, let me just kind of move this out of the way. Let's go to page 172, and then later we'll pick back up where we had left off. Now, when we used the LDA a little while ago, right, on the bottom of page 165, the reason you'd use that is a process called direct alkylation of esters and nitriles. It's some of the easiest chemistry to understand, so long as you understand basically what's happening with LDA. So I have 4 examples, 3 on page 172, 1 on page 173, of direct alkylation of enolates. So kind of follow along with me. It's really easy to understand. Now recall that LDA is lithium diisopropyl amide. Okay, you don't need to know its structure necessarily, but just remember it's a really strong base. But what else? It's a hindered base. Okay, so the fact that it's hindered means it's not going to attack the carbonyl, can't get to it. It can only attack protons that are mildly acidic or very acidic, but in this case mildly acidic. So let me just show you some examples. This is a lactone. Lactones are cyclic esters, okay? And as long as you have an alpha hydrogen, you can do this, and we have 2 of them, right? So this is step 1 in the process. All right, write this down. This is step 1. Step 1 is to remove one of the 2, in this case 2 protons from what? The alpha carbon. So get used to writing the letter alpha. What does that do? It makes an enolate. I'm going to write that in. This is an enolate. Now, enolate stable? Well, they're resonance stabilized. What I'm showing you here, though, is the enolate form that acts as a nucleophile directly. So, square brackets means you haven't isolated it. This is in your flask. So what are you going to do in the lab? In the lab, you're going to add electrophile. Okay, what's going to happen next? This carbon's going to attack there. Then what? Then that. What do you call that? What do we always call that? This is an SN2 reaction. Okay? So look at the overall process. So where you formerly had a hydrogen, you've now replaced it with a methyl group. So that's why it's called a direct alkylation. So if you can do an SN2 reaction on it, you can choose any electrophile that you want. Now, does it have to be a lactone? No. Here's an ester. Okay, you can alkylate esters just as easily. The only thing that really matters here is that you have a carbonyl. Okay, and we do. And that on that carbonyl you have an alpha hydrogen. You only need 1. So we're going to use LDA again. What step is this? This is step 1. Tetrahydrofuran is a solvent. It's understood we're doing it at a very low temperature. What do we get? We get an enolate. We have an enolate formation. Now, the enolate that I'm showing you is the one that actually would be the nucleophile. This is resonance stabilized, but we're not going to alkylate the oxygen. We're going to alkylate the carbon. Now, carbon is a harder nucleophile than oxygen, so that's why this happens. And there again, you have your SN2 reaction. So these are very much alike in some ways. Okay, so we used to have a hydrogen there. You replace it with one of these methyl. So this would be a direct alkylation example. Now, does it have to be a carbonyl? Not necessarily. Y'all remember what that was called? Okay, that's called a nitrile, right? It's a nitrile. Now, what do nitriles and carbonyls have in common. Okay. T-R-I-L-E. Okay. Nitrile. You can barely see the R there, but it's nitrile. They're both electron withdrawing groups, right? They're both EWGs. So it behaves much the same. As long as you have alpha hydrogens. So this one works pretty good. So this is kind of like an enolate. Okay. Enolate. I'm going to write enolate-like because there's no oxygen involved there, but it's still an enolate. This was step one, just like before. And here it is. It's in your flask. What are you going to do now? You're going to add electrophile. In this case, methyl iodide. So again, we see an example of an SN2 process taking place right before our very eyes. So this is really good chemistry. It shows you how you can replace alpha hydrogens with alkyl groups, provided the reaction can undergo SN2. Now let me show you one more along those same lines. And I've chosen one that's kind of special, not to suggest that the others aren't. But this will help you understand the chemistry a little bit better. Okay. Notice here we have a ketone. This would be a 2-methylcyclohexanone. So it's not symmetrical, right? So here we have an alpha, and here we have alpha, but this is, I'm going to call it alpha prime. Why? Because they're a little different. This has a methyl attached with a hydrogen. This has 2 hydrogens. Now remember that LDA is a strong base, but it's also hindered. Okay. So where is LDA more likely to attack? At the alpha prime position or the alpha position? Well, there's a lot of chemistry going on here. If you said the alpha position, you're right. Okay? So long as we keep this reaction really cold, okay? Let me write that in. It needs to be kept cold, right? Minus 78 degrees. And you add just a little less than an equivalent of LDA. In other words, if you had 1 mole of that, you'd need about 0.95 moles of this. Then the dominant enolate is going to be this one. Okay, so I'm going to write more here. More meaning there's more of this enolate than that one. I'm going to write less here. More of that one, less of this one. Why? This position is what? Less hindered. So the less hindered spot results in forming the more predominant enolate. So there's more of this enolate coming from the less hindered position. Now, if this is not kept that cold, or if you add an extra bit base and you let it equilibrate, that's going to convert into this. But that's a story for another day. You don't have to worry about that in sophomore organic chemistry. So this was our step one, just like before. So step 2 is to add your electrophile. And I chose methyl iodide every time, but you don't have to. Obviously, any reaction that would fall under SN2 guidelines is fine. So you can see why this is your major product, because there's more of this, because there's more of that. There's less of this, and there's therefore less of that. And these could be separated very easily by distilling them. So this is direct alkylation. Let's see if we can finish this, and then we'll go back to where we left off previously to finish up the chapter. Show how you might prepare the following compound using direct alkylation. All right. Well, to understand this kind of problem, you need to locate the alpha. You need to locate the alpha position. So I'm going to go ahead and sketch a hydrogen in there and put the letter alpha, because I know originally there must have been 2. Right, 2 alpha hydrogens there, right? Because that's how this chemistry works. So there's our lactone, right? And while I don't have to do it, I'm going to sketch these 2 in anyway. Okay. And again, this is a 2-step process. What's the first step? The first step is LDA. Now, if you just write in LDA, fine, you're good. If you want to indicate the solvent, I'll write things in green, THF. That's even better. And if you want to mention the temperature, that's really good. Okay. But at minimum, you need this 1 here, and you need the letters LDA. You don't have to draw the structure. So that's going to remove a proton, right? One of the protons from the alpha carbon. It's going to generate an enolate from this particular lactone. Okay? And then in step 2, that's when you add your electrophile. Now, identifying the electrophile is pretty simple. You just have to find the group that was added. Okay? So we have an aromatic ring, and then there's a CH2 right here. So let's go ahead and sketch that. And then I'm going to sketch my aromatic ring. Right, and there's a methylene. So there's a CH2 here. And you have a choice of leaving groups. It could be a halogen, bromine, chlorine, iodine, tosylate, a bunch of them. I'm just going to go with bromine, right? So this would get you to that end result, okay? All right, so that's a simple direct alkylation reaction. Let's do another one kind of like that. The next one doesn't have oxygen. It's not a ketone, it's not a lactone, it's none of that, but it has electron withdrawing group. And that's all that really matters. So you know that there's a hydrogen here, right? And there must have originally been what? 2 hydrogens. So why don't we go ahead and sketch this thing minus this alkyl group. Then we'll be able to see really clearly how we're going with that. Okay. So that's an alpha carbon in effect, and here's your nitrile. You can just write the letters CN, or if you want to draw it out with a triple bond, you can. So that's good enough. But if you want, you can also sketch in these hydrogens like I have. All right. And then, what is step 1? Step 1 is what it always has been, LDA. If you want to show the solvent, you can, tetrahydrofuran. And if you want to show the temperature, -78, you can do that as well. It's certainly not necessary to do that. Step 2, you simply need an electrophilic species. We're going to count the carbons. So we have 1 here, okay, 2, 3, 4, 5. It's a 5 carbon chain. So we need N-pentyl bromide or something like that. So I'll let you figure out how you want to sketch that. You can draw a zigzag structure if you prefer. You can use any good leaving group. So we need a 5 carbon unit though. There's 1, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5. All right, so that would get you that product. So this is organic synthesis using direct alkylation. Now I have one on the bottom. Okay? This is a synthesis problem. It's an outline of synthesis of the following compounds, beginning with gamma-butyrolactone. Okay. Now this is not gamma-butyrolactone, right? This is just cyclopentanol. So I'm not sure why I have that there. No. Oh, with cyclopentanol. Pretty interesting. I wrote gamma-butyrolactone. That compound right there, that's gamma-butyrolactone. What a coincidence. Anyway, cyclopentanol. Okay, let's just do a forward reaction on this. Okay, in other words, just go straight forward, okay? We know we need to get a carbon on there, okay? We can get either one of these. So how do we get that on there? Using direct alkylation. How could you do that? Well, one way would be to use LDA, and we need a source of methyl group. How about methyl bromide or methyl iodide? Either one's fine. What's that going to do? Well, owing to symmetry, right? Owing to symmetry, we're going to replace one of those four hydrogens, in this case, with a methyl group. Okay, so we're getting close. What would we want to do next? Well, somehow or another, we need to establish a double bond between alpha and beta. How do we say that we could do that? Y'all remember? Well, one way to do that is alpha bromination. Okay? Alpha bromination. So we can add bromine, elemental bromine, Br2, but we need a solvent. And the solvent we're choosing would be acetic acid. You could write the word acetic acid, or you can just put its formula beneath it. But by virtue of doing that, okay, what do we now have? Well, we know we had a methyl group on there, but we also know that this position is more substituted than that position, so now we're also going to have a bromine here. Okay? So here we have 2-bromo, 2-methyl cyclopentanone, and we want to finish this up. Okay? Remember how to do that? Here, let's go ahead and use what we did before. Let's use pyridine. And let's heat it up. All right. Now, both of these are formed, okay, by E2. They both form as a result of an E2 reaction. This is the major product, though, this one, and this is minor. You'd have to separate those by distillation. And the reason this is major because it's the more stable, more substituted double bond. This is less stable, less substituted. But there's an interest in both of these. So this would be how you do that. So you think we've come to the end of chapter 22 notes. It seems like we have. However, we skipped over a big portion of that. So I need to go back with you, I think, to page 166. And on page 166, we can start taking a look at the stuff that I had skipped over with you. All right, so give me a few seconds here. Situated. Okay. Rubber gloves make it hard to move the paper around. Okay, here we go. All right. Now this next set of notes, guys, is something we haven't seen before and some things that we have seen before. All right. Some of them I'll kind of let you read on your own, but I do want to go through the major parts of it. Folks, this is a halogenation of enolate ions called the haloform reaction. Okay, this is something we used to do in lab. We could still do it if we could go to lab. But what we do here is we're going to take something like a methyl ketone. Right? So what's a methyl ketone? This is the methyl ketone, right? Because it's a ketone with a methyl group. And we're going to add a halogen. We're going to put the pH very, very, very high. And so what happens is that we're going to convert this into sodium carboxylate. This is the sodium soluble carboxylic acid. And more specifically, this is a haloform. And haloforms tend to precipitate, so this would be a test for a methyl ketone. So, for example, this is chloroform, CHCl3. Chloroform. And if it was bromine here, it would be bromoform, iodoform. Okay, these are the different haloforms. So this reaction is specific to methyl ketones. It can work with secondary methyl alcohols. In the old days, these did a qualitative test to figure out if you had a methyl ketone. The products are carboxylate ions, that, and a haloform, this. And if you use iodine, you produce what? Iodoform. And iodoform is a really easy to spot because it'll precipitate out as a yellow solid. So we could do that in the lab if we could go back to lab. Anyway, that's all I wanted to say about that. Let's pick up on the more important parts of this remaining chapter 22. We'll talk about the reactivity of enolate ions and alkylation, which we've already done, but we're going to look at a few other ones. Okay, the following reactions involve alkylation of enolate ions. One's called the malonic ester, one's called the acetoacetic ester, and the one we just did, okay, was direct alkylation of ketones, esters, and nitriles. Okay, we've already done that one. Okay, so we've done this one, but we haven't done these two. So the general mechanism to make an enolate, right? Okay, however you make your enolate. Then, okay, that was it from step 1, and in step 2 you add an electrophile. Okay, then you do the SN2 reaction, so you end up bonding a carbon and whatever it has attached to it. So we're relegated to the rules for SN2. So this is a direct alkylation, but all of these are going to work the same way. Now, let's flip over to page 167. On page 167, I indicated that you may want to review your chapter 11 notes, okay? We talked about a lot of these things as it relates to this particular type of chemistry. But let me just remind you folks about this. The least hindered electrophiles get faster rates. In other words, if you were doing the reaction on methyl iodide, okay, versus, say for example, isopropyl iodide, who's going to go faster? Okay, who's faster? This one, because it's less hindered. Okay, the better the leaving group, the faster the rate. The carbon bearing the leaving group should be sp3. Even though, and this is something I want to point out now, even though polar aprotic solvents are best for SN2, in this part of the chapter, you're frequently going to see ethanol, which is polar protic, as a solvent. But don't be alarmed. That's okay. The alkylation reactions generally involve 2 steps. One's the enolate formation to generate a nucleophile, followed by step 2, addition of an electrophile. Okay, so we're going to look at 2 classic examples of these. And the first one's called the malonic ester synthesis. And the reason it's called that is because we're going to use malonic ester. So the overall purpose of the malonic ester synthesis is to convert an alkyl halide or tosylate or something with a leaving group to a carboxylic acid that contains 2 additional carbon atoms. Here's what I mean by that. Here's your alkyl halide, ARX. You're going to conduct a malonic ester synthesis, so where you used to have X, which is your leaving group, you're going to replace it with that group there. Okay? And you can actually do this reaction 2 times, where you end up having 2 different or 2 identical R groups there. And I'll show you how to do both. The first general reaction, case 1, we call that monoalkylation because we're only going to add 1 R group. This is malonic ester. Okay? This is malonic ester. Now you say, what's so special about malonic ester? What's special about it, and you can't really appreciate it until you draw the structure out. I'm going to draw it out here in a slightly different fashion. That's my alpha carbon, right? So we're going to label the alpha. And let me sketch in something here. Okay? I'm redrawing malonic ester so you can appreciate the chemistry behind it. Malonic ester has 2 ester functionalities. Okay? So in effect we have 2 electron withdrawing groups bonded to the alpha carbon. Okay? So there's alpha. Now, why does that matter? That means those protons are especially acidic. You have a pKa of around 9 or 10, so it's easy to get them off. You don't need LDA. You don't need that strong of a base. You could use LDA if you wanted to, but we don't need one that strong. So what we're going to do, okay, here we are. We have this is malonic ester, but I've redrawn it like that in simpler form. This is step 1. Step 1 has always been and will always be the formation of an enolate. You're not going to isolate the enolate. Okay? You generate it and leave it in the flask. Step 2, just like with direct alkylation, you're going to add an electrophile. And the enolate will act as a nucleophile towards the electrophile. So think about what happened. Where you used to have a hydrogen, you now have an R group in accordance to SN2 rules. So that's why this is called a monoalkylated malonic ester. Now, step 2, we're going to kill 2 birds with 1 stone. Okay? here we're adding acid, and this is for hydrolysis of the esters. Or you could call it ester hydrolysis. Okay? But we're also heating it, so that would speed up the hydrolysis. So not only did the heat speed up the hydrolysis, but it also facilitates decarboxylation. Decarboxylation. Okay, so you do basically two things in one. So what does it mean, hydrolysis of an ester? It means if you just hydrolyze the esters, okay, if that's all that you did, then this intermediate here would be a dicarboxylic acid. Let me just sketch it like this. It would be CO2H, CO2H. In other words, that would be hydrolyzing both ester groups into their corresponding carboxylic acids. So that's why we're producing two equivalents of ethanol, right? So that's what the acid is for. This is a catalytic quantity of acid. You're heating it, which speeds up the hydrolysis, but once you get to this point, you heat it further. Okay? Now, I'm not going to go through the entire mechanism with you. McMurray has that. But once you have this dicarboxylic acid, okay, one of these groups, either one, is going to break off. And that's why you form CO2. Okay, so that's the decarboxylation step. What is your ultimate product here? Your ultimate product is that one. Okay, contrast that with the beginning compound. They're very different, aren't they? They have the same carbon backbone, only now, where you used to have a hydrogen here, you've got an R group of your choice, and you also converted one of these esters into a carboxylic acid. So this is called monoalkylation of malonic ester synthesis. So let's see if we can go a little further. Let me work one of these with you, okay? I left a lot on here, but I'm going to show you how simple this can really be. It says, show how you would prepare heptanoic acid. There's heptanoic acid, okay, using a malonic ester synthesis. Say, whoa, we're going to go from that to that? Yep, we are. Okay? We need to know how to do that. But it always involves, the same sequence of reactions. Now, I encourage you each and every time to use the letter alpha, okay? Because you have to find that letter alpha, carbon alpha over here. And where is it? Be careful, it's that one. It's not that one, it's that one. That's the alpha carbon, okay? Now, why is that critical? Because it's what's attached to alpha is going to determine the nature of your electrophile in step 2, okay? So you're going to have to count those carbons. Well, let's go ahead and do step 1. Now, this is a synthesis, so you don't have to show the intermediates, okay? You do not have to do that. You don't have to show the intermediates. You don't have to show the ionic intermediates, what I meant to say. You only have to show the covalent intermediates. So what was step 1? Step 1 was to do what? Was to generate an enolate, right? How do we do that? We're using sodium ethoxide, NaOET, sodium ethoxide, and we're using ethanol, which, by the way, is a conjugate acid of that particular base, as a solvent. Now, if you want to place the charges above it like that, be my guest. But it's understood that this is an ionic compound. So that's going to take off one of these protons from the alpha carbon, one of these two protons, make an enolate. But you're not isolating the enolate. You're not. Nope. You're going to add something to it. That's why it was important we highlighted this. Let's count the carbons. 1, 2, 3, 4, 5. So we need a 5-carbon unit with a leaving group on it. Have we seen that before? How about a bromine followed by a pentyl group? Okay, 1, 2, 3, 4, 5. That's all you need to do. Now, what will this get us to? This is going to get us to our first covalent intermediate. Okay? Now, I do a zigzag structure there, but I'm going to draw the condensed structure here Just looks a little bit cleaner. The important thing is that we have the right stuff written down on the page. So there's my 5 carbon unit. All right. And what else will we have there? Nothing else on the molecule changes. Nothing changes. Okay. This is still an ethyl ester. ET for ethyl. And there's still a proton there. So this compound here can be distilled, isolated, characterized by NMR, IR, mass spec, all that different stuff that you would normally do in a lab. Can. Now I'm not showing the byproducts here because they're not important to us. Folks, after you've done the alkylation, the last set of reactions is the same. We're going to add acid. Okay? Probably in lab it'd be something like sulfuric acid. Okay? And we're going to reflux it. Now what does the acid do? It hydrolyzes the esters to carboxylic acid, but you're heating it to speed up the hydrolysis, but you're also heating it to carry out the decarboxylation. So this step here, okay, what does it do? That step produces the 2 equivalents of ethanol from the hydrolysis, and it produces the 1 equivalent of CO2 from the decarboxylation, but more importantly, it produces N-heptanoic acid as our organic product. Okay? Now, let's go a little bit further. This looks pretty similar to what we have on the previous page. The distinction here, folks, is that it's a dialkylation. We're going to do this reaction a second time. So just like before, we're going to have our alpha carbon. We're going to add sodium ethoxide and ethanol, produce an enolate. This is step 1. We're going to add electrophile, okay? And we got our monoalkylated malonic ester. There it is. You can isolate that. But what do we know about these protons? They're acidic, right? So why don't we do this reaction again? Let's do the same set of reactions again. So this was step 1, this is step 2. Let's repeat step 1. Okay, let's do step 1 again. Okay, so we formed an enolate here. Let's call this enolate 1. This will be enolate 2. Enolate 1, enolate 2. So we're adding the base again. We're making another enolate. We're adding an electrophile again. This electrophile can be the same as that one or identical, or it can be different. As long as you can carry out what? An SN2 reaction upon it, you're going to alkylate. So here we have dialkylation, where you used to have 2 hydrogens, you have 2 R groups. Again, they can be the same or they can be different. The last step is always the same. Okay. Here you're going to conduct the hydrolysis with acid. You're going to heat it, and look what you end up with: a di-substituted carboxylic acid. So that's why this is called dialkylation. Okay, let's try one of those. Let's try one of those. Now here, guys, what do you always want to do? Find your alpha carbon. Find it over here as well. I hope you did. Let's highlight the R groups. We have a methyl and we have a propyl. Now, I made a note here. This will require the use of 2 different alkyl halides. Okay. In this case, we have a methyl halide and a propyl halide. And generally speaking, the bulkier halide is added first. Okay. So we're going to put on that group first. You did it the other way around. That's okay. But it's because of the rules for SN2 reactions. So let's go ahead and work this one out. Okay. Step 1's the same. We're going to add sodium ethoxide, NaOT, it's a strong base. We're going to use ethanol as our solvent. Step 2, we're going to add the propyl group. Right, I'm just going to write it propyl, and I'm going to use bromide. Okay, we could use chloride, iodide, tosylate. The list just goes on. Let's go ahead and sketch our first intermediate. The first intermediate that you get, again, you can isolate these by way of distillation. Okay, all you've done is replace 1 hydrogen, okay, on the malonic ester, so the rest of the molecule hasn't changed. So what hasn't changed, I'm going to sketch with the blue marker. CO2, ET, CO2, ET, hydrogen. And I'm not showing the byproducts, okay? We don't need to do that. All right, now, you're going to add the second R group. How do we do that? Just like we did before. You need to add sodium methoxide again. And you need a solvent, ethanol. And then now, you got to count the carbons. Oops, there's only one. So we need a source of methyl groups. I'm going to choose methyl bromide. Okay, now what does it look like? Now what it looks like, it's not that different than before, only you replace that other acidic proton, okay, with the methyl group. So let me sketch that in here as we go. Alright, so the things in blue are the same as before, minus that one proton. Right. Did I do that right? Yep. Okay. And then what did I say the last step always was? Yes, you know to add acid. And you know to heat it. So that would give you this particular organic product. So this is called dialkylation. All right, let's go ahead and finish up. The next reaction is almost identical. Okay. Hardly any difference, only now we have a different name because it's going to give us a slightly different product called the acetoacetic ester synthesis. Right? And here, instead of making a carboxylic acid, you're going to end up with a methyl ketone, right? Or a dialkylated methyl ketone. But these look a lot alike. It looks a lot alike. This, guys, is acetoacetic ester. Okay? And again, what's it for? Is to make these complicated alkylated or dialkylated methyl ketones, right? So step one is pretty much the same as you saw before. I'll write that in. This is step one. Step one is to add the strong base. Now it's going to selectively go after one of these alpha hydrogens, right? And not the ones on the methyl group. Remember why? Because these have a pK of closer to 10, whereas the pK of that is closer to like 18 or 19. So these are much more acidic. So that's why these get abstracted. So let me put a prime here. This is much more acidic. Therefore, this is our enolate that we get. In step two, we add electrophile just like before. You now have a monoalkylated acetoacetic ester. And guess what? Just like before as well, with melodic ester, you have acid, you have heat. That's going to result in the loss of this ethyl group. You're going to hydrolyze the ethyl ester, and you're also going to lose the, you're going to decarboxylate, and henceforth there's ethanol, the hydrolysis product, there's CO2, the decarboxylation, and you have made your monoalkylated methyl ketone product. So in effect, where you used to have a hydrogen, you now have an R group, and so this is a more complicated methyl ketone than what you had originally with the acetoacetic ester. So let's do one of these. It says show how you prepare 2-heptanone using the acetoacetic ester synthesis. What Greek letter am I about to sketch? Alpha. Now there's alpha 2, but now which one though has the most acidic hydrogens? Is that one, right? So I'm going to put a prime on this one. Those are more acidic because this alpha carbon has 2 electron withdrawing groups on both sides. It's going to make these protons dramatically more acidic. Now, so that alpha carbon is going to correspond to this alpha carbon, not that one. So count the carbons to the left of that. Looks like a 4-carbon unit. So it's simply incumbent upon us to install that. Step one, we've seen this a gazillion times already, is a sodium methoxide with ethanol. And in step two, 1, 2, 3, 4, a 4-carbon unit with whatever leaving group that you want to put on there. Bromine seems to be pretty popular. Okay? And that's going to get us to what? It's going to get us to our first monoalkylated acetoacetic ester. So this whole molecule is intact, minus this one proton or that one. Okay, so let me sketch that in with you. So here's the alkyl group that you added, the butyl group. And like I said before, the rest of the molecule remains intact. Okay, all the things that you see there are still there. Right, so there's that alpha carbon, here's this hydrogen. There's the methyl ketone on that side of the original acetoacetic ester. Here's the ethyl ester. Right? So you're going to take care of those rascals in the next step. And what is that final step? You've seen it before. The first step is ester hydrolysis using acid. Okay? And that's going to hydrolyze this ester to a carboxylic acid. You're going to speed that process up by heating, but you're going to continue to heat beyond that. So we're going to end up losing this entirely. So here's your final product, and these are the byproducts. I think I pointed that out before, that these are the byproducts. I'm not sure I did. Don't worry about the byproduct, but just be aware that we've accounted for them here. Now, you probably guessed where we're headed next. We're going to do a dialkylation. Okay, so we'll do one of those, and we're really wrapping this up pretty quickly. So this is the general reaction for dialkylation. Kind of go through that quickly. All right, here's your alpha carbon. You're going to make an enolate. We'll call this enolate 1. And this is the enolate that we would get from acetoacetic ester after step 1. You add your electrophile, the SN2 reaction. You now have a monoalkylated acetoacetic ester. Okay. We're mindful that this proton is acidic, way more acidic than those three there, so we can selectively remove that proton, generate an enolate 2. And enolate 2, we add an electrophile to it, we conduct an SN2 reaction, we get our, in this case, dialkylated acetoacetic ester. This stage, you hydrolyze the esters, you heat it, and you end up with your final dialkylated methyl ketone product. Let's try one of those. So look at sample problem 22.08. Here's acetoacetic ester, and what we want to do is we want to convert it into 3-methyl-2-hexanone. All right, let's go ahead and label these alpha again. Promise me you'll do that. I'm not putting an alpha there, and you know why. And let's find our alpha. Okay. So here we have to put on a propyl group and a methyl group. We're going to put the propyl group on first because we said you generally add the larger group. But if you go the other way around, it's not that big of a deal. Okay. I'm going to go ahead and add sodium ethoxide as my base to make the enolate. We're using ethanol as our solvent. Okay, we're heating it in the lab, and we're going to put on a propyl group. I'm using a condensed structure to draw my propyl group. This is propyl bromide. Alright, we're going to draw the next covalent intermediate. And what would that look like? It would look like the original acetoacetic ester minus one of the alpha protons. Okay? So where you used to have this proton, you replaced it with this propyl group. But again, the rest of the molecule is the same as it always was. So these monoalkylated species can actually be purified, okay, characterized to ascertain that you've generated that. That is an intermediate. So these are very stable products, okay? Alright, so you did that one day in the lab, and the next day you come back. So what are you going to do when you get back to lab? Well, I'm going to put on a second R group. And you know how to do that now. You first have to take this proton off. And you're not going to have any trouble getting it off, because the ethoxide is sufficiently basic for that. Okay, sodium ethoxide. Notice I've written it the other way around, but however you want to do it. And you have ethanol as your solvent. Step 2, we have to look at what group was added. We have a methyl group there. We're going to go to the shelf and we're going to find some methyl bromide. Okay? and that's going to give us what we need. So we're going to get another intermediate that we can actually isolate, characterize, prove that we have it. Okay? We can take an NMR of it, we can take an infrared, we can do all the things that we had did with the other ones, just as if it were its own compound, because it is its own compound. Right? Alright, so there's a methyl group there. Right? Switching all these colors around. CO2, ET, right? Getting a little sloppy, I'm sorry. And there's that. World's ugliest 3 right there. That's a methyl group, CH3. And finally, we know what to do. We're going to go ahead and add our acid, H3O+, and we're going to not forget to heat it, otherwise we're not going to get decarboxylation. And so ultimately we end up with this dialkylated methyl ketone. It's really cool. And to get a racemic mixture of these, even that carbon's chiral, you get a mixture of both the R and the ethene enantiomers. Now, here's the last one, okay? And we'll be done. Sample problem 22.09. Now this was a little different, but not so different that we can't engage upon doing it. Here we're trying to make a ring, okay? But you have to be careful because you have to realize, okay, that the carbon here is the alpha carbon, that alpha carbon. So how do we put a ring on there? How do you put a ring on there? Well, you can't do it directly, okay? You kind of have to do it indirectly. And what I mean by that is we're going to count the carbons in our ring, and that'll be the size of our carbon chain that we're going to add to begin with, okay? So those, we have a 4-carbon unit. So we're going to have to conduct the SN2 reaction intramolecularly here.
Mm-hmm.
So really it all boils down to the design. Step 1, we've seen it many times, sodium ethoxide. Let me write it this way, okay? Ethanol is our solvent. Now we're going to spend a little more time talking about what we need here, okay? We need a 1, 2, 3, 4 carbon unit. So watch what I do. I'm going to sketch 4 carbons. No big mystery there. And how about though this time I put leaving groups on both ends? Let me just choose bromides. Okay? Now, what's going to happen? Well, notice this is symmetrical. We're going to do an SN2 reaction, and we're going to replace one of these 2 hydrogens on the alpha carbon, just like before, with this group, with one of them. Now, this is symmetrical, so it doesn't matter which end we attack. So the nucleophile can attack here or here. Let's go ahead and sketch that out. I'm going to start with a bromine on this end, okay, and then I'm going to work progressively towards that end. We're almost done, guys. Okay? So you've displaced this bromide, that bromide, and the rest of this molecule is the same. How many times have you heard me say that? So you've done a monoalkylation. The distinction here is you have a bromine on one end. Okay? So let me sketch that. And there's that hydrogen. Now, what did you do before? You replaced that proton, right? You did. How did you do that? You added sodium ethoxide. Okay. So what that's going to do, it's going to convert that into an enolate. Okay, I'm not going to sketch the whole thing. This is going to be an enolate. That carbon is going to enolate, right? So it's a negatively charged carbon. It's a negatively charged carbon. And what's it going to do? It's going to do an intramolecular, okay? This carbon is going to come here and attack intramolecularly, displacing the bromine. That's how you make the ring, okay? So intramolecular SN2. So that's how you produce a ring. So the ring's going to look like this. Okay. And that group's still going to be there. And this again the compound that you could isolate. So count the carbons. We have 1, 2, 3, 4, 1, 2, 3, 4 part skeleton here. And what do you always do at the end? You have to add your acid, and you have to heat it. And what will that do? What that'll do, it'll hydrolyze this ester. It'll also decarboxylate spontaneously, and ultimately you have this compound. So understand that one's a little bit harder than the previous ones, but dwell on it for a little while, and I think it'll make perfect sense to you. At least I hope it does. Anyway, we're done, guys. That's it for chapter 22. We're almost finished with the course.